I was out on a run one day in Tucson, and I came across this animal on the trail. The image here is converted to grayscale, and it's cropped to 1024 by 1024 pixels. What if you were measuring this image, but you could only keep half the pixels? Which pixels would you choose, and what would the impact be on the image? Here's an example where you say, well, okay, I'm going to keep the left half of the image. Here in contrast is what happens if we subsample. So we're going to keep 1/4 of the pixels. We took every fourth pixel vertically and every fourth pixel horizontally. Doesn't look like much has changed on this scale, but if we zoom in to the region on the back of the snake, we can see that there's some major differences in the detail in the images. We have many choices in subsampling. For example, we could randomly select half of the pixels. So here, half of the pixels in the image are set to 0, and the others are the original value. Now, I could show you this image with half of the data missing, or we could fill in the data. For example, if we take the example where we didn't sample a block of the image, we could fill in with some kind of content-aware fill. So here I've used Photoshop to fill in the square that's missing. And you see that it looks plausible, but it's not quite the true image. Here, in contrast, I used an algorithm we'll discuss in episode 16 to estimate the image from the missing data. So it looks pretty reasonable that we filled in the missing data in the center image, but if we zoom in, we see that the restored image is not quite the original, although displaying this process data is a lot better than just leaving the missing pixels missing. How we subsample makes a big difference in the results. Suppose, for example, we randomly sample half of the data in the Fourier space rather than real space. So we put our mask of ones that was zeroing out half of the Fourier space. The image we get looks like the original. Zooming in, we see the original structure plus some artifacts. Today's discussion and the next several episodes deal with strategies that have been used in this challenge of how to estimate data where the data has been corrupted by the measurement system. Which data to measure is the design of the forward model. How we estimate the scene is the inverse problem. We looked at shift invariant models in episode 13. Let's look at shift variant models today. Computational imaging. Episode 14, linear regression. Back in episode 13, we looked at shift invariant systems, and we found the Wiener filter as a optimal filter for minimizing the mean square error in the spectrum of the signal. Today, we're going to consider the similar problem, but we want to consider shift variant systems where we have this algebraic model for our forward model, G equals HF, and we want to minimize the regression error. So we're going to minimize if we take our estimated signal f sub e and operate it on it with the forward model, we want the mean square difference between that and the measured signal to be minimal. So we differentiate with respect to the estimated value, and we can solve then for our estimate from the derivative of this error function and get that the estimated signal is the inverse of the conjugate forward model times the forward model times conjugate with forward model operating on G. This estimator is called the ordinary least squares estimator. It's built into common software, so if we go into NumPy, for example, in the linear algebra library, we can run the least squares operator to recover a signal from a forward model. In this case, we've assumed a random bipolar forward model and made some measurements and then operate on it with the least squared operator, adding, as you see here, some random Gaussian noise to the signal, and we see this reconstruction. The covariance from this operator has this form. It's the variance of each individual signal times the inverse of the H prime H matrix. So recall from episode 7 that we analyzed these shift variant systems using features coming from the singular value decomposition of the forward model, and we could estimate each of the features individually corresponding to its singular value. So this G tilde is a reconstruction of the measurements on the basis function of the singular vectors of the forward model. Each term had this form that if we project then each coefficient or projection onto the basis functions of the forward model is the singular value times the corresponding basis or the corresponding coefficient in object space plus the dot product between that singular vector and the noise. So the signal to noise ratio that we have in estimating this f sub n, the coefficient on that singular vector, is proportional to the singular value divided by the inner product between the noise and that singular vector. So we get a lot of noise from signals that have small singular values, where the SNR is very low. So what we could do is say, well, we want to eliminate those sources of noise. So rather than project the object, or rather than try to estimate the object on the full basis or the full state of the object space, we say we're going to limit our estimate to the coefficients of the object space where the singular values are large. And to that end, we could build a reduced forward model where we take the singular values over some threshold and build, just to make a diagonal matrix of those singular values over the threshold, and build this matrix from their singular vectors. So lambda sub r here would be, or the reduced singular vectors where we've truncated the singular vectors that we're keeping, and we build still an m by n matrix where m is the number of measurements and n is the number of coefficients in the object space, but on a reduced basis. So what's called the Moore-Penrose pseudo-inverse is estimating f from this reduced basis. And so what will happen here, of course, is that normally this term, the noise term, would be dominated by terms with small values of lambda. But if we've only kept values with lambda above some threshold, then this term remains reasonable. And we now have what's a biased estimator. We've only estimating f on the support of this reduced singular vector, but our noise has been substantially reduced. So we need to choose what our threshold is for the singular value. But if we do this, we have the hope of estimating a signal with reduced bias, or with reduced noise. Now, this is formalized in a more systematic way with what's called the Tikhonov regularization, which is the shift variant system analog of the Wiener filter. Now, instead of just minimizing the regression error, we would minimize the regression error plus the total energy in the signal. This lambda naught squared is a parameter that we use a regularization parameter that we use to decide how much we want to damp out the small singular values in the reconstruction, and this FE, we've projected FE on the L2 basis. And so we take the minimum with this with respect to FE, and we can solve to find that our estimate takes this form. So normally, of course, when we would project FE onto the singular values with the inner product between the singular vectors and the measurements, represented then on the singular value basis divided by lambda sub I. But now we've added this term out front, lambda sub I squared divided by lambda sub I squared plus lambda naught squared. So if lambda sub I is much larger than lambda naught, this term would be 1, and this would be the normal inverse. But if lambda sub I is small, then this term goes like that small value divided by lambda naught squared, so it would go to 0 and damp out the small singular values. Here's some results when we do that. Now we've increased the noise level compared to what it was in the earlier estimations. So the ordinary least squares estimate now becomes very noisy. But if we implement the truncated SVD with 900 elements in the SVD, we see that the most of the noise here is coming from the terms with small singular values. So that noise is greatly eliminated, and the signal reconstruction looks interesting. We would find artifacts in this, but the artifacts may be hard to find if the singular values are not well correlated with the structure of the signal. So this is similar to what we saw in the introduction, where we looked at eliminating terms in the Fourier transform, eliminating in an orthogonal space to the representation space of the image. Doesn't necessarily cause structural artifacts that one can see. And so in this case, the truncated SVD is very reasonable. And you see that the Tikhonov approach does a little bit better. Tikhonov and both truncated SVD and Tikhonov have parameters that one must choose. In the case of the truncated SVD, one needs to choose how many elements to keep. In this case, the forward model is 1024 by 1024. And we've dropped the last 10%, the last 124 terms. In the case of Tikhonov, we've selected this regularization parameter lambda naught, so you'd have to tune that to your liking in implementing the systems. For the particular matrix that was used here, this is the singular value spectrum, so dropping the last 124 terms involves truncating here, so that you only keep 900 terms in the inverse matrix, and that drops this last 124 terms with singular values that are below 10% or below, and then most of the noise presumably is coming down here where the singular values are near zero, so one could even keep a few more terms. So with that truncation, again, this is the kind of reconstruction that one sees. This again is this very spiky spectrum of an ion from this Chianti database. Of course, results would differ depending on different signals, and so you should go and dig into the Colab notebook that accompanies this and try different signals and different parameters in these reconstructions and see what happens. So that's a regularized least squares estimation, and we see that we get some improvement. Next time we're going to try another look at regularized least squares using a convex optimization, and this is the kind of results that we'll see. That here's a noisy Tikhonov estimate of the spectrum, but if we use this lasso algorithm we'll talk about next time, we can do better.